Okay, now we want to expand on this using the Bohr model and looking at this effective nuclear charge or core charge. The two factors that affect how closely an electron is held to the nucleus. One is what charge do they see from the center of the core, and then how far away are they from that charge. So we're going to explore that again and kind of look across some extra materials. So what we've had, let's just review where we started on the first part, looking at hydrogen and helium. So they're in the first period. So the first period is filling the first shell, and so the first shell only holds two. So hydrogen has one electron, one proton, and so it had an ionization energy of about 1.31, right? 1.31 megajoules per mole. So, and again, the ionization energy is how much energy does it take to remove that electron? It's attracted to that positive proton, so it's going to take energy to take it away. How much? 1.31 megajoules per mole. The helium has an extra proton. Two protons is helium, and of course those protons would repel each other, but there's some neutrons in there kind of keeping this thing all together. So now the positive charge has doubled. The attractive force should roughly double, and it did. It takes 2.37 megajoules per mole to take an electron. That almost looks like a plus. That's a negative. Take an electron and remove it from helium. So much stronger attraction. That's a very high ionization energy. And helium is not going to let those electrons go. And then we come across, then we said, well, lithium is right here. That's the start of the second period of the periodic table. What's going on in the second period? We're starting to fill the second shell. And how did we know? What evidence do we have that one of the electrons in lithium goes into the second shell, not the first? Is because, well, with three positive charges, if all of the electrons minus were in that first shell, the attraction would actually be stronger. And we've done experiments on it and reviewed it, and we found that it's 0.50 megajoules per mole for lithium, or sorry, 0.52. So it actually got weaker. So we say the only way that could happen, let's take, so two of them still are in there, because we have found that taking a second electron from lithium is very difficult. And let's put one of those electrons in a second shell. So lithium now, it's three electrons, 1, 2 in that first energy shell. We're calling them shells, but it's an energy level. The second, the third is in that second shell. So we've begun to fill the second shell. And then of course we come across to beryllium, and we put that, the second one in the, or 4 valence electrons, 1, 2 in the first shell, 2 in the second shell, and the ionization energy data fit. Notice what also happened. So lithium, just to look at what's happening coming down. So hydrogen has 1 electron in its outer shell. It only has 1 shell. Lithium has 1 electron in its outer valence shell. Look what happened to the ionization energy. Hydrogen was 1.31, much stronger than lithium. What's the difference? So lithium still sees +3, and this is that lampshade shielding. So +3 minus the 2 shielding inner electrons equals +1. So they both see a +1 charge. Effectively, they see a +1 holding them in. But lithium has now been removed farther away. So it's farther from that charge, so, and therefore the attraction is weaker. Okay, I want to skip ahead. And then in the previous video, we also looked at beryllium. But let's skip ahead to nitrogen. Nitrogen's right in here in the second period. Nitrogen has an atomic number of 7, so it's got +7 charge in the nucleus, 7 protons. 2 electrons, I'm going to put them as E's. 2 electrons in the first shell. So that means it has 5. 1, 2, 3, 4, 5 electrons in that third shell. So now I'm starting to build up all these electrons in the valence shell, 5 valence electrons. What do they see? +7 minus 2 they see now a +5 effective charge, but they're out there in that second level. And so what's happened to their ionization energy? Ionization energy for nitrogen is 1.40. Pretty strong still, so it's hard to take those electrons away. So it's holding them on. So the energy it takes, 1.40 megajoules per mole to take an electron from nitrogen. It's held very strongly together. So that would be our nitrogen. As we come in across what's happening, the positive charge they see, the effective charge for lithium was +1. The valence electrons on beryllium only saw a +2. Now we're coming over here, it's now +5, so it's building. And then let's skip one over and let's go to fluorine. So fluorine is right in here, almost to the end of the second period. It's got a +9. 2 electrons in the first shell. 1, 2, 3, 4, 5, 6, 7 in that second shell. Second shell is almost full because we found through data the second shell is full with 8. So this is fluorine. What does it see? +9 minus 2 equals +7 effective nuclear charge. So what's happening? The positive charge that they see is building greater and greater and greater. Fluorines, those electrons are held very, very tightly. In fact, what fluorine tends to do is it will take an extra electron from somewhere out here. I want to not be off the board. Let's say I got another electron out here. It's going to tend to add that to have a full valence shell to form the fluoride ion at single minus. So fluorine really has an attraction for electrons. Look at that big positive charge that those valence electrons see. So it's really pulling them in quite a bit. So they get strong. That attraction to electrons, the attraction of atoms to their valence electrons, they're pulling them in. It increases as we come across. And then the last one there, neon, +10, electron, electron. 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So the 10 electrons, 2 in the first shell, 8 in that valence shell. So now neons really, look at the positive charge that these valence electrons see. So there's 10 positive charges being shielded by only 2 inner electrons. +10 minus 2 equals +8. Big positive charge. Those electrons are really being pulled in tight. They don't go anywhere. The other thing that neon has is this is a very stable arrangement. That full shell, both shells, the first and the second are full. There's no need for it to add another electron to fill that shell. A full shell is a very energy favorable situation. Atoms will always interact with other atoms to fill that valence shell, or they'll just empty it. And of course, this is a very high ionization energy, IE equals 2.08 megajoules per mole. So that's big, right? So it takes a lot of energy to take an electron from neons, and so neon just stays put. It's a noble gas. It doesn't react with anything. It's set. I want to look at just one more atom, and let's draw it over here. And then I have a handout where we're going to go through the third period. But let's start the third period with sodium. Sodium's right here. We say, well, I mentioned that, well, the second shell is full with 8 valence electrons. How do we know? Well, here's how we know. Sodium has +11. We've already determined through looking at lithium that the second shell must only hold 2. The first shell holds 2. 1, 2, 3, 4, 5, 6, 7, 8. Let's look at it temporarily. Well, what if I put that 9th electron? So 11 protons. I need 11 negative charges if it's a neutral sodium atom. If I put it in here, they would see +11 minus 2. That would be +9. That would be a huge ionization energy. So it would be even bigger than that. So we say, well, if I'm putting that one there, then the ionization energy for sodium would be really strong. But in fact, sodium's ionization energy is only 0.50 megajoules per mole. So it's very low. So that says, hey, to take sodium, I've got to take one of these electrons, bring it out here, and put it in a third shell. So that's the only way that we could have such a low ionization energy. Now, so what does this valence, so now my valence shell has now become the third shell, right? So both of these are now the inner shell. So the third shell is now my outermost, or my valence shell. So how many inner shielding electrons? Before we said there's two. Why was there only two inner shielding electrons? I was in the second period, so the only inner shell was the first shell. Now, how many inner shells, looking at from his perspective out here, how many inner shells? Well, there's two of them, and that makes 2 plus 8. There are 10 electrons now closer into the atom than this outermost shell, right? So when we're subtracting and counting shielding electrons, how many electrons are acting as that lampshade, shielding the positive charge? All the electrons that are more inside the valence shell. So 11 positive charges, that's big, right? But now I've got 10 shielding electrons, so this guy only sees a +1. It's very loosely held. Sodium in nature, because of such a low ionization energy, it always ejects that electron and becomes Na+. So when we find sodium in nature, it's a very common element, right? Table salt, sodium chloride. It's always Na+ in nature because that electron is so weakly held that it just goes away. So we're going to continue with the Google document on looking at the third period and what's going on. So what's happening is I'm coming away, as I'm coming down the periodic table, I'm adding shells. Those electrons are starting to get further away. What's happening as I come across the periodic table, electrons are starting to see bigger and bigger positive charge. They're more tightly held. And we'll expand on that as we go.